Let's look at two questions related to conservation of energy. The first one is your turn. It's a race down the incline. We have different shapes. So even if they have the same mass, same radius, because of the different shape, they will reach the ground at a different time. So if it's a hoop and a disc, which will reach the bottom first? So you can try this, and I actually used to do this in class, where I would bring canned goods, for example, a can of beans and then a can of refried beans. So the distribution of the mass was different, and that affected which one got to the bottom first. So the way that you want to think about this conceptually is think about, first of all, which one has the greater moment of inertia, because the greater the moment of inertia, the harder to rotate. So that's going to hinder it going down the incline. So the hoop has the higher moment of inertia because the mass is distributed further away than the solid disk here. So what this means is that they both start with the same amount of gravitational potential energy because they have the same height. But since the hoop has the greater moment of inertia, that means that it's going to have a greater rotational kinetic energy, 1/2 I omega squared. So what this means is that all of the gravitational potential energy, most of it will be converted to rotational for the hoop versus the disk. The disk has a smaller moment of inertia, so it'll have less rotational kinetic energy, so the disk will have more of the translational kinetic energy, 1/2 mv squared, which will make it reach the ground first. So the object with a smaller moment of inertia is going to reach the bottom first. If this didn't make a whole bunch of sense to you, we can actually also look at it with an example where we're actually going to work it out with the equations to see how it works out. So this is a sphere rolling down an incline, and we want to find the speed at the bottom of the incline. So this is a conservation of energy problem, and we'll write out the equation, the kinetic energy initial plus the rotational kinetic energy plus the gravitational potential energy initial equals the same quantities for the final, KEF plus KERF plus PEGF. Conservation of energy, we cross out what's equal to 0. The sphere is starting from rest, so it has no kinetic energy period. The V equals 0, and the omega initial equals 0. So it has no kinetic energy. And then when it reaches the bottom, it has no gravitational potential energy because it has no height. So we're going to write down the terms that remain. We have all of the gravitational potential energy that it has initially is converted into the two types of kinetic energy, translational and rotational. So when we're trying to find the speed at the bottom, we have to remember that the angular speed is related to the linear speed. We have the relation v equals r omega. So we cannot just solve for vf in terms of all the other variables because omega has to do with v. So what we're going to do is we're going to get rid of omega. Omega equals v over r. So we're going to plug that in here so that we can get v by itself, because it says speed, so it's talking about the linear speed, because it did not specify angular or rotational. So I make that substitution. So I have 1/2 mv final squared plus 1/2 I, and then omega f is v over r. So that's vf over r, and that's whole omega is squared. So that means you have to square the v and the r. And now we can solve for vf. We're going to factor it out on the right-hand side. So we'll have mgy initial equals 1/2 m plus 1/2 I over r squared. and all of that times Vf squared. I factored out Vf squared from both terms. So we do need to know what is the moment of inertia of a sphere. And if you go back to the table that I had in the moment of inertia video, you'll see that the moment of inertia of a solid sphere, we're going to assume it's solid here, doesn't say otherwise, is 2/5 mr squared. So since I used a little r for the radius here and a little m for mass to be consistent, I'm just going to write it as 2/5 mr squared. That's the moment of inertia of this sphere. So we're going to plug that into for I here and see what happens. We have mgy on the left side equals 1/2 m plus 1/2 times 2/5 mr squared, that's the I here, divided by r squared. So you see that the r squared is actually going to cancel out. All of this is multiplied by v final squared. I know this looks like a lot of math, and it is a lot of math, but it's going to look very beautiful once we finish. We have 1/2 m plus 1/2 times 2/5, so you multiply across to get 2/10 m. So you see it's already starting to look better. Now we have to combine our coefficients here, 1/2 plus 2/10. Well, 1/2 is the same thing as 5/10, so 5/10 plus 2/10 equals 7/10 mvf squared. And we're almost done. Now we can see that we can cross out the mass. The mass doesn't even matter. In the previous question, the masses were the same. The mass does not even affect the speed. Just like in free fall, the mass doesn't matter. What we see that matters is that factor of 2/5, which that depends on the moment of inertia. How the mass is distributed is what's going to affect that final speed. Now when we solve for Vf, we have to multiply by 10/7 on both sides to get rid of the 7/10. And then that gets us Vf squared, and then we have to take the square root. So that's our final answer. We don't have any numbers, so we'll just leave it at this. The y initial is the initial height that we are given of the incline. The point of this problem is that the final speed depends on the moment of inertia. So if this had been a different number, let's say that it was going to be a hollow sphere, then we would have put 2/3 here instead of 2/5. And it means that we would actually have ended up with a smaller speed at the end, because you see how it gets flipped here when you solve for v. So it turns out that the object with the smallest moment of inertia is always going to win the race because it's easier to rotate. So it's going to win. It's going to have a faster speed at the bottom. So that's the end of this video. Just to recap, when you have rotational energy because you're rotating and you're rolling, you can use conservation of energy. Just don't forget to include the term for rotational kinetic energy. I tend to like to ask conceptual questions for this topic here, where we're going to have objects that are racing down an incline, and you just need to look at the moment of inertia to see which one has the smallest, which one has the mass distributed closer to the center, and that's the object that's going to win that race.